right, good afternoon, everyone. Welcome to today's lecture where we'll start with ray tracing, which is, of course, a little bit different than the projective method. So it's a kind of a new chapter we are starting up here, which is also why I think we should take the opportunity and have a little look at current state-of-the-art computer graphics, because we're focusing so much on the basics here in this course that it gets a little bit lost, at least in the lectures. So let's just, for fun, look a little bit into the state of the art in computer graphics. And of course, the best place to go is, of course, to the movies. And yeah, so I have a little clip here. All right, so I'm not affiliated with them, and I don't get any money from them for showing this here. So don't get the wrong idea. If I would be working for them, I would probably make much more money, believe me. Yeah, so it's just a little fun thing also to show you. And of course, this is way, way beyond what we cover here in the course, because yeah, we're really focusing on the very, very basics here. But the point is really that all these techniques that they use, these are really the basic, are built on these basic techniques that we were discussing in this course so far. So I hope the next time you watch a movie like that, you're not only just enjoying the movie, but you also have a much better appreciation for the computer graphics. And if you see, for example, some, I don't know, a marble or a nice sky image, you probably think about also, yeah, maybe they have done this with Perline noise, and yeah, I know how to do that. So it's also kind of a nice thing. But of course, a lot of you are also are not just interested in movies, but you're mostly interested in computer games, because a lot of you are game technology students. So I also have a little clip from the related video game here. All right. Yeah. So like I said, when you watch these kind of things now, I hope that you're not only just enjoying the game or the movie, but you're also kind of starting to look more into the computer graphics. And of course, I was not just showing this for fun, but also to kind of illustrate something here, which I'm pretty sure you can, some of you already know or can guess. If you compare the graphics with the video game and the movie, of course, you see that there is a huge difference in quality, which is, of course, because the movie can be pre-rendered. It just has to be rendered once, and then you have it on the movie, and then you can send the movie to the movie theater and play it as often as you like. Whereas the computer game, of course, has interactivity, so you're interactively changing the graphics based on the player's action, which means you have to do a real-time rendering, which is, of course, way more challenging, and of course limits the possibilities that you have, which is also why this real-time rendering is usually done, of course, with the hardware support, like you did in the practicals when you did the shader programming. Whereas, for example, at Pixar, they also use a pipeline, a graphics pipeline similar to the built on the basic principles that we discussed here, but they use a software implementation. Of course, they use a lot of hardware as well, and I don't really know what exactly they're using, but there is actually quite some information about them on the website. If you go to their website, they have a research section there, or there's a research Pixar website where they also publish some papers about their techniques. So the point is, of course, yeah, we can do this in a pre-rendering step, and then, of course, we can put much more effort into making the graphics way more complex than when we do it in real time. And the reason why I brought this up here is not just because we are entering a new chapter now with the ray tracing, but of course also the ray tracing, we said this already at the beginning, why we're focusing so much on the projective methods here and less on the ray tracing in this course, because the ray tracing is per default an approach that is usually much slower than the projective methods, which is why, for example, in computer games, usually you don't use ray tracing, although this is actually a changing trend now, because there are, of course, a lot of approaches also to make ray tracing faster. Good, yeah. So we already talked quickly about ray tracing at the very beginning. So what I did now is I just copied and pasted a few of the slides from the very beginning. So you should all know this. That was one of the introduction slides in the very first lecture about projective methods. And now you know all what is all behind those words, how these techniques hopefully work. Hopefully you know that. We model our scene with objects, for example, triangles. Then we project those triangles towards the screen to get a 2D representation of it on the screen, and then we put some color and some shading on those triangles with all the different techniques that we discussed, and of course many more that we didn't cover here. And now with ray tracing, I also already said that the situation is basically just the opposite of what we're doing with the projective methods. With the projective methods, we have a scene, and then we look at each object in the scene and project it towards the screen, and then calculate how it looks on the screen. For the ray tracing, we look just in the opposite direction. We take the position of the observer or of the virtual camera, then we look on one pixel on the screen, and then we think about, okay, what do I have to draw in the pixel? What color do I have to give this pixel to represent the scene that I have modeled, the 3D scene that I have modeled behind the screen? And that is, of course, the color of the pixel that is hit by just continuing this ray from your eye towards the pixel. So it's, if you remember how we explained the perspective projection, where we have to project the points to get a perspective, a perfect perspective. Of course, we said we project it towards the eye, and here we're doing the opposite way. We're looking from the eye to a pixel and then towards the scene, and then the first object that we hit is, of course, the one that we see on the screen. Unless, of course, it's a transparent one, then we have to continue on our ray. If it is not transparent, then we can put the color there, the color of the object, or if we do the shading, the color of the light that is reflected there. So what we do then here is the same as with our simplified shading model. We calculate the normal vector at this position, and then we reflect this ray. So we're following up this ray, and then, for example, if there is another object here, let's say there is a triangle, then of course it gets reflected again until we reach, for example, this light source here. And then we know, of course, that the color at this point, which is then the color we draw on the screen, is influenced by this object here, is influenced by the reflection from this object, which in turn is influenced, of course, by the light color. So you see here that we're basically doing the same thing, but in the opposite direction. And you also see here that we have this possibility of including the recursion in the ray tracing, which is why ray tracing on the one hand produces so very realistic images, because we have the whole shading integrated in this process, and not just simplified, but really with recursive following of rays. But this recursive following, of course, is exactly the reason why the standard implementation of ray tracing is so much slower than the perspective projection. Yeah. So yeah, I pretty much already said that these characteristics of ray tracing, and why we actually originally, when I took over this course, the focus was much more on ray tracing, and the practicals especially were purely ray tracing. So you had to implement a ray tracer from scratch. And that shifted now when we introduced this game focus in the bachelor, because we said, of course, for game programming, it makes more sense to let you do shader programming. But of course, a lot of these, so these are just some examples. I think I already showed them in the first lecture. And these are examples then that we have from the last time that we did the course with ray tracing programming in the practicals, and then we switch to the shader programming that you're doing now. But of course, ray tracing is still part of the course. Just because I put it now at the end of the course doesn't mean it is less relevant, because even if you're only interested in real-time rendering for computer games, ray tracing is important. First of all, like I already said, there are trends towards real-time ray tracing, so there are approaches to make ray tracing faster, and there are actually computer games who already use ray tracing or use a combination of ray tracing and projective methods. Path tracing is a method or a trend that is also related to this, that is very popular. But even if you don't use it for the graphics, the techniques that you use in ray tracing, this shooting a ray towards a pixel and then shooting it towards the scene to see which is the first object it intersects with, is important, or has always been important with projective methods also, because if you have interaction and you, for example, click on a pixel on a screen, of course you want to know which object are you clicking at. So if you have a second object here, and you're clicking on the screen on one pixel here, then of course you want to follow, you can follow the ray and then see, does it intersect with the blue or with the red circle to cause some action by the player. So this is of course one thing where you use these ray tracing techniques also in real-time rendering games or real-time rendering graphics. And of course a lot of the techniques that we use in ray tracing are also used in projective methods. In fact, if you remember this simplified shading model that we had at the very beginning, that was from the book, from the chapter about ray tracing. So we're using the same simplified shading model, or we can use the same simplified shading model in both approaches, the projective methods and the ray tracing. And there are a lot of other techniques that are pretty much the same from the basics, but then we just need to look into a little more of the details or a little more twists in those techniques or changes. So a lot of the things we will discuss today for ray tracing are actually just repetitions of things that we have already done, now just applied in a little different way to this ray tracing approach. Yeah, so I already said they share a lot of techniques. For example, the shading models, how we already talked about how to calculate intersections, which is of course very important for ray tracing. But there are also major differences because we have a different basic concept or basic approach to it. So for example, for ray tracing, we don't need the perspective projection because we're going the opposite way. We're looking at the scene with a certain perspective, and that also implies that we don't need to do a special hidden surface removal with the set buffer or so, because of course we're looking at the scene from the camera position, so we do not look at the object, so we don't need to specify the order that the objects have with respect to the camera, because we're looking from the camera, and then obviously we always hit the first object that is closest to us. And of course the most important difference is, like I said, that we're not going through the objects and put them on the screen, project them on the screen, but we're going from the perspective of the observer and then go pixel by pixel and look onto the screen and look then and from the pixel we look at the scene to see how the color changes, which kind of seems like now that actually ray tracing might be faster, because of course even if you have a lot of pixels, the number of pixels is limited, whereas your scene can have a huge amount of triangles. But of course the important thing is to keep in mind that the ray tracing looks at this recursively, so for each pixel, in the worst case, we have to really look at each object that we have in the scene, whereas for the objects, we just go through the objects once. So this is then, of course, why it's clear that the ray tracing per default is usually the slower approach. Good. So, like I said, we already have basically all the tools and the material to build a simple ray tracer. If we want to do that, we will need to look at each pixel, and then for each pixel we compute a ray that we shoot through that pixel and then continuing towards our scene. Then we look into try to find the intersection point with the first object that is hit by this ray. We need to calculate the surface normal, because then we can do the shading and put the color of the pixel on the screen. So this sets the color to the value computed from the hit point on the screen. That is of course not really including this typical recursive step that we have in the ray tracing. So this is of course just a very simplified initial implementation of it. But let's go through this step and see how we can do that. And like I said, we already know all these kind of tools. The question is now, how do we apply them in a way that is most appropriate for this situation? So shooting a ray is of course clear. From a position, we model this with a line, and we talked about line equations. Of course, we also talked about different line equations. So what would be the most appropriate here? If you look at the scene, it seems kind of obvious that the parametric linear equation is the most obvious one, because then we can take the eye position as a support vector. So E here is our support vector. And then we shoot a ray towards the pixel on the screen. So we make a vector to the pixel on the screen, and then we use just the difference between these two vectors as our direction vector. So S minus E is then our direction vector. And if you remember what we had and of course we could choose any vector on the line as direction vector, but choosing it this way makes our calculation quite nice and smooth and simple, because if you remember what we had, I think it was in the very first or in the second tutorial, we talked about the characteristics of this parametric representation of a line. There was one exercise that asks you, what do we get when we have t equals 0 and t equals 1? Or it was asking what kind of values do we need for t to get the support and the end of the direction vector. And then, of course, the answer is if we have t equals 0, we're at the I position here. If t equals 1, we are at the screen position. And for all values t larger than 1, those are the values where we're basically shooting our ray at the scene and are interested in finding the intersection. So you see that by choosing this, it becomes very nicely fits into this model that we have with the screen and the I coordinate and the t between 0 and 1 within that distance. Now I said that the projection, of course, is something, the perspective projection is something that we don't have to do in the ray tracing because we're going in the other direction, and when we shoot the ray towards the scene, the perspective is automatically preserved in the right way. But there is one step from this process of making the perspective projection that makes it that we can use here to our advantage to make the calculation easier. And of course, this step is, as you can probably guess, this that we say we put a coordinate system around the camera, around our I vector. Yeah. No, the vector S is the vector to a pixel on the screen. From the origin, yeah. This is the origin, and these are basically your world coordinates. Like in the perspective projection, we had the camera coordinates and the world coordinates, and this is the world coordinates where all these points are represented with respect to them, and also your screen. In the other case, we had a view frustum, and here we just look at the screen because we don't need a view frustum, are represented with respect to that. And then the pixels on the screen are described by this vector. And now we want to do, of course, describe it with respect to the camera, because then, of course, our calculation again becomes easier. And this is now where we create this camera coordinate system. And we do this in the very same way as we did with the perspective projection. So we first define this view up vector. I hope you remember the view up vector was a vector that basically splits our head in two halves and then points somewhere up, and we just need that to create a vector that is perpendicular but parallel to this to the viewing direction, and that is perpendicular to the viewing direction and parallel to the screen. And then we make the cross product of those two vectors, and then we have our coordinate system here, which has all the right angles here. And you see here I used minus W because per default, or very often, we make the convention that we want to look in the negative direction because then we get a right-handed coordinate system. But again, this is of course just a convention. We could also say per default we want to look in the positive direction, and you get a left-handed coordinate system. Another thing, of course, we don't have to have to make sure that we don't forget. We usually want to have a normalized vector, so the calculation becomes easier. So we divide by the length of the vectors, and then we have our normalized camera coordinate system in a similar way as we had it before. And now, of course, we want to express. First of all, of course, we. For the perspective projection, then we specified our view frustum with that. Here we don't need the view frustum because we're not, like for the perspective projection, we needed to look into, okay, what are the objects that I need to project now on the screen? And those are exactly the objects inside of the view frustum. So we had to specify this area and also clip the triangles that were partly outside of it. Here we don't need that because we're just looking through the screen at the scene, so the screen implicitly defines the area that we are looking at, which is why we just need to specify the screen, but we do it in a similar way as we specify the view frustum, only we don't have a near and a far plane, but we have a top, a bottom, a left and a right, not plane but side in this case. And of course these values can then be expressed. The distance is of course a value that we set per default, which is then minus w, because we're looking in the negative w direction. And now we want to, of course, express those points, exactly those S vector points that you were asking about. We want to express them with respect to our new camera coordinate system. And that is quite simple because we had this already before. We basically just need to map these abstract left, right, top, bottom values to the size of our window or of our screen. We can do this. This is a very simple scaling, like we had it also with the perspective projection, by just taking one side here and divide the abstract values by the concrete pixel value, which is then the nx and ny. And last year I filled in for one of the tutorials about this, and then I realized a lot of people had problem with this L and B. Why do I have to add L and B? And that's why I came up, I added this simple example here. First of all, to illustrate that, but also to kind of make a point. When you're looking at something in the exercise, or when you're repeating stuff and you see a formula and you don't understand it, very often it helps to just fill in some numbers and look at it with a concrete example. That very often makes it much, much easier. Or if you have a 3D case, try to draw a 2D case of it, and that very often makes it much easier to understand. Because if you look at here, if you, for example, say our left side is at minus 500 and the right is at 500, and our pixel window, let's say, should have 100 pixels, then of course you're mapping 1,000 pixels to 100 pixels. So for example, if you are at 1/4 here, 25 pixels, then you would assume you would end up at 250 pixels. But of course, since we are going from minus 500 to 500, we have to start here. We're not starting here by 0, but we're starting at minus 500. So what we have here is we do not have to map R minus L to this nx, but we have to map L plus R minus L to this nx. And when you do this, then you will see here that we have here a minus 250, which is of course the correct value. And of course this plus 0.5 is something that I'm often kind of, not ignoring, but I'm not really mentioning it explicitly, because this is then, of course, because of the concrete implementation here. When we're dealing with the pixels, then we're dealing with the pixel centers and not with the cell with the vertices on the cell or on the grid corners, which are of course expressed in integers. So then we have to just add this 0.5 to it. Good. Yeah, so this is a simple window transformation like we already had it a couple of times. Just again, we have to look into the very concrete case, and then there are just a few little details that are a little bit different. But if you do this carefully, then or with an example, then it's usually quite obvious how this works out. Good, yeah, and then we can express the points on the screen with this coordinate system. We have the origin of the coordinate system, and now we can, of course, construct our rays that we shoot through a particular pixel on the screen. And of course, the origin of this ray is the support vector that we used for the line before. That is our vector E, which is then is now the origin of the new camera coordinate system. And the direction is then, of course, a vector from that position through that point on the screen that we now expressed in screen coordinates. So if you look at it, the mapping from the left-right to this pixel grid is exactly what we did here in the UY direction. So what we do is here we go the distance to the screen, that is this part here, and then we go UY in the direction that we just calculated. So this is the u times the u vector, and this is v times the v vector with the u and v like we calculated it here. And then of course we end up at this point here, and then we know that we can shoot our ray through this point here. That means we can express it with this equation, which is a standard parametric equation, with this being the support vector and this being the direction vector, only now expressed in camera coordinate system. The reason why I've chosen alpha here and not t like we usually do with parametric equations is that I realized that there might be then confusion with this t value here. So that's why I've just chosen alpha. Good. Yeah, so now I said that for ray tracing, we don't need to make this step of this rather complex step of creating this perspective projection matrix that we do for the perspective projection, where we basically make this trick of making the perspective projection, multiplying it with the matrix to be able to make an orthographic projection, which is much easier to make. So we are saving this step here, but of course there might be a situation where we also want to have an orthographic projection with ray tracing. Like I said, there are computer games or situations where you can imagine that an orthographic projection might be better. There are often like technical drawings that are using orthographic projection. So of course there might be situations where we also want to do it with ray tracing, and of course we can do this. The difference is just how we shoot our rays towards the scene. So if you remember from the perspective projection, what we said when we do the orthographic projection, we do a parallel projection where all the projection vectors are perpendicular to the projection surface. Whereas for the perspective projection, they were all moving, pointing towards this one point where we had our camera. And that means if we want to create our arrays now, we just have to create an array for each pixel on the screen that is perpendicular to this screen, which means all rays have the same direction vector, but it also means all have a different origin vector. And the origin vector is, of course, a vector where the u and the y value are exactly the position on the screen, the u and the y values of the position on the screen in these screen coordinates that we calculated. So this is again the same formula that we had before, the u and the v for the calculation of a point here. So this is the uv vector, uv0, and then of course we do the direction vector. As direction vector, we take a vector that is parallel to these here, and that is of course a vector that is parallel to the viewing direction, so we can just take minus w as direction vector. And that gives us then our equation, again a parametric equation, but now a parametric equation that we can use to do the orthographic projection. And if you compare those look very similar, but of course the important thing is you have to look at the variable here that we have here. Here the variable refers to the whole vector here, whereas here, although we have pretty much or exactly the same vectors actually, the variable here only refers to this one. So this is the direction vector in our case for the orthographic view, and this is the direction vector for the perspective view, whereas this here is then the support vector in the respective cases. So you see here the formula looks almost identical, but just where you put the brackets then decides if you make a perspective projection or an orthographic projection. Which also, as a side note, is a comment related to what I said last time, that I'm always telling people try to really understand what we are doing here and to visualize those formulas that we have here, because if you really need to memorize all those stuff, that's going to be very, very hard. But if you understand the concept behind it, then it's much easier to memorize it. Or if I show you this formula, you can more easily then identify it and explain it and use it And that is, I just want to mention this because quite often sometimes someone comes to me and asks me, well, there is so much stuff we have to memorize in this course. There's so much material, and what's the point of it? I can look this all up on the internet when I'm implementing. Why do I have to memorize this? But the point is, I don't really want you to memorize it letter by letter, or at least not everything, because in a lot of situations it's really, if you memorize the approach and what it represents, then you can come up with the formula automatically, even if you don't remember it heart by heart and letter by letter. And that is, of course, also why we're not allowing you to use books in the exam, not because we want to test how well you are able to memorize, but we want to use this. We were basically assuming that most of you are not able to memorize all that stuff, but if you understood the concept behind it, then you should be able to write it down and come up with the solution. Good. All right. So now we have the viewing race, and as you saw, everything we did here was stuff that we have done before. So it was just the way how we applied to this particular situation was the interesting question. And the same, of course, goes for the intersection. We already calculated intersection points, and usually what we do when we calculate the intersection of a line or of a ray with a surface, we represent that surface in the implicit form, because then we can just put the parametric representation of the line into the implicit representation, because then we only have one variable here left. And then we can solve for this variable and then put the variable in again into the parametric equation of the line, and then we have our intersection point or intersection points. I have to say intersection points, of course, because with some objects we get more than one intersection point. For example, with the sphere, and I think I can quickly go over this because I hope you all remember it. With the sphere, if we represent it in that way, where we say the implicit representation, you probably remember that we said a point is on a sphere if and only if the distance of the point to the center of the sphere has the same length as the radius of the circle. And if you write that down formally and bring everything to one side, you come up with this formula. And then if you put the ray into the formula and try to solve it for t, you see that you have a quadratic equation here, which we can solve with this equation here, and then we get 0, 1, or 2 solutions, depending on if this value under the square root is negative, 0, or positive. Another thing that I think I mentioned it at that time, that was but that was probably not that clear to many why I'm mentioning that or why this is important, is that if you have two solutions, of course, one of them can also be negative. And of course, that can happen quite often in ray tracing, because in ray tracing, we very often we have always the origin at the eye position. And then, of course, if we have a sphere around the origin, then, of course, we are always inside, and this left part always becomes negative of our solution. Good. And of course, the same goes for intersection of rays with a plane. If we want to intersect a ray with a plane, we can use the implicit representation of the plane, put the parametric equation into the plane, and then calculate the intersection point, or calculate the value t of this intersection point, and then put it in the line equation, and then we have our intersection point. Now, of course, very often we're not interested in intersection with planes, but intersection with triangles. As you see here, I already drew a triangle here. And of course, one of the options to do that is, I hope you remember the barycentric coordinates, is to calculate the intersection points and then represent a triangle in barycentric coordinates, because then we have a few conditions that we need to check to verify if the point is inside of the triangle or not. And this is now a point where, which I think is quite nicely, because it basically just uses stuff, a lot of things that we have done before, but in a way that you realize now makes the calculation actually quite nice and quite simple. And that is by not taking the implicit representation of the plane, but taking a parametric representation. Of course, we can also calculate the intersection point by using two parametric representations, not only the line, but or the ray, but also the surface. And if we do that, we set them equal to each other, and then we see, of course, we have here three variables. So remember, one of the characteristics of a parametric representation was that we have always one variable less than the dimension we are in. So in 2D, a parametric representation had one variable. In 3D, it has two variables. So for example, for the sphere, we said we had the two parameters are the two angles, the longitude and the latitude. And for the plane, it was that we had two direction vectors on the plane, and then each parameter indicated the distance we have to go on each of the direction vectors. So we see here we have a linear an equation with three parameters, and those are all linear equations. So we have a linear equation system with three equations and three unknowns, which we can solve with Gaussian elimination. So what we do is we can solve this by calculating the intersection point and then check if the calculating the intersection point with the plane, and then check if the intersection point is within the triangle. And the plane we can represent by the vertices of the triangle. We can do this, for example, by taking A as the support vector, and then B minus A and C minus A as the direction vectors. And then we can write down the plane in parametric representation. So beta and gamma, and that is wrong. Beta and gamma are the parameters, not the vector, so that's a typo here. And of course, if you remember barycentric coordinates, then you see that this is exactly the same way how we define the barycentric coordinates, which we can also use that, of course, to define a plane, like the yellow one that I indicated here. But if we use it as barycentric coordinates, then we get this this grid where each cell has a parallelogram shape, which we can then allows us to very easily do this test here. So in this case, we're just using it as a line, but of course, I have purposely chosen the direction vector in this way, because then later we will see that this leads to our barycentric coordinates, which will then make our calculation much easier. But for now, we're just looking into a plane, so we want to solve this linear equation system to get the intersection point. So we have on the left side our ray, on the right side we have our plane. And now if we bring all the variables on one side, we see here beta, gamma, and t, then we can write this as a linear equation system in matrix notation. We can create the augmented matrix and solve it by Gaussian elimination and get then a solution for all these variables we had in here. And now I hope some of you are already seeing what's the nice thing about this. Normally we would calculate the intersection point and then do this test if then represent it in barycentric coordinates to do this test if the intersection point is within there. But this representation in barycentric coordinates we already did implicitly by choosing the plane equation in the right way, that it is basically the same as the representation in barycentric coordinates. So by solving this linear equation system, we do not only get the t value that we need for the intersection point, but we already get the beta and the gamma value that we can use for a test in the first place to see if the intersection point would be within the triangle, and only if it is within the triangle then we have to calculate it. Good. So you see here, this is all stuff that we already covered, but it is fits kind of very nicely and very smoothly together now. And of course, another thing we already covered was the calculation of the surface normal and then the lighting. Like I said, this is something I'm really not going to again, because there is nothing different here, because the simplified shading model that we discussed at the beginning was actually taken one-to-one from this chapter about ray tracing. So we talked about the ambient shading, which we repeated also last time, and talked about radiosity, Lambertian shading, and the Phong shading, which creates then these nice spots here. So these are examples actually from the practicals that we had the last time when we used the ray tracing. Now, of course, I'm always showing these nice heads that you are creating with all these special effects. But these were also kind of really nice images that they created with ray tracing then. So yeah, and this is a summary of the basic ray tracing algorithm. So you see, with all that you learned so far, hopefully you are already able to implement a ray tracing algorithm, although we haven't really covered it so far in the lecture, but you would have been already able to implement it before the lecture. Good. So yeah, you already saw it. This is the basic ray tracing part. Now we are moving to the advanced topics, which also fits quite nicely to the break. So are there any questions? If not, then 15 minutes break. All right.